Okay, this is page 3 of midterm 1, and not gonna lie, this is gonna be a little bit harder at the beginning because this first question, number 3, A, involves drawing 3 different resonance contributors for this molecule right here, and you have to rank which one is the most important minor contributor and which ones are 2 other significant contributors for resonance, but not as significant as the most important minor contributor. Because this one, the one that I had circled right there, that's the major contributor. It's the best one. There's no charges. Everything has full octets. Like this is the normal resonance contributor, I guess. And then there's going to be other contributors for resonance. So we're going to just draw all of them and then we're going to rank which one is going to be the best out of these not so good ones. But they're all significant, so we have to recognize all of them. So let's start. So remember that for resonance, you can draw electrons going from pi bond to pi bond. You can draw electrons going from lone pair to pi bond, or you can draw resonance going from pi bond to lone pair. So let's just write that at the top. So we can go from pi bond to pi bond. We can go from lone pair to pi bond, obviously right next to the lone pair. You have to draw the pi bond because it's that p orbital that's contributing to this resonance. And then we can go from pi bond to lone pair. Again, it has to be right next to it. We can't go from lone pair to lone pair. That doesn't even make sense. You're just going between molecules that just, yeah, that's not resonance. So, so one version is just like moving these electrons from this pi bond onto this oxygen. I don't know if that's the most important minor, but that is one of the minor contributors, is just having a plus charge on the carbon. Oh, here, I guess we don't have to explicitly draw on that carbon. A plus charge on this carbon, and oxygen with negative, and this oxygen, and then R. And then there's going to be a positive here. But, okay, so we see that there's a positive on this this carbocation, and, well, I guess there's a carbocation. But there are a couple ways that we could move this positive charge. We could move this pi bond here, or we could move 2 of the electrons onto here. Obviously, we could draw 2 of the electrons back onto here, but that just takes us back to the major resonance. So we're not going to consider that one. But we can do either of those. So let's start with one at a time. So one of them is basically going from a carbocation right here to a carbocation here by moving the pi bond, or moving the electrons that are in the pi bond. So that will look like this, where it's R prime. We've got a carbocation, and there's a pi bond there. Oxygen, still negative. Oxygen, and R. Okay. It looks like these two are about even. I mean, they both have a carbocation, they both have a negative charge on the oxygen. These two aren't too different from each other. So let's try that other example where we talked about moving the lone pair from this oxygen. Here, let's do this in a different color. Actually, let's move this all up a little bit so that we can fit that all right here. I'm not necessarily answering which one is the most important minor contributor yet. We're just drawing out different options for resonance. And then we'll figure that out. So, because that's what I actually did during the test. I think I erased a whole bunch because I tried to guess which one would be the most important minor, and then I was wrong, and yeah. So, now we're going to draw the one where we move the lone pair from this oxygen here. And that'll be that. And we're ignoring this black arrow right here. The pi bond's still gonna stay there. There's a pi bond there. Oxygen with a negative. Oxygen, and then R. And this oxygen, instead of having 2 lone pairs and 2 sigma bonds, it has 2 sigma bonds, a pi bond, and a lone pair. And so that's actually going to have a plus charge. Okay, so let's see. There's other like really, really minor resonance where you could move the pi bond onto the carbon, or you could move it onto this carbon, so then they'd have like a negative charge on the carbon. That's not like particularly great. We would rather have a negative on an oxygen than on a carbon because it's more electronegative, and carbon ions just we don't typically make them, at least in this part of the class. So let's see, are there any other major resonance? Well, let's see. We could also move that pi bond there. No, sorry, we wouldn't do that. Sorry, that doesn't make any sense. We would have to move the electrons there and then either move the lone pair onto the carbon, which, like we said, we wouldn't want, or move it back here, but that'll just bring us back to this resonance right here. So, yeah, I think that's about it as far as the major or the most important minor resonance. So, which one is the best one? Well, resonance, the best resonance still has full octets on everything. And so even though this pink one right here has a plus charge on an oxygen, and typically we'd rather have a plus charge on a carbon than an oxygen if we can help it, it's also the only one of these resonance contributors that has full octets. The ones with the carbocation, the carbons each only have 6 electrons. It only has, let's see, it only has this one and this one and this one. There's 2 electrons in each of those sigma bonds, and it has no lone pairs, so it has a non-full octet, and a full octet would have 8 electrons. And so this pink one, even though it has a plus charge on the oxygen, it's going to be the most important minor contributor. That's a mouthful to say. Okay, so we're just going to move these ones down here so we don't have to redraw it. And we're going to put that here and change it to black. I guess we can leave it the same. And let's see which arrows would lead to this structure, because when we were drawing this structure, we did it from this one. So, oh, that's not the same color. So let's say what arrows will lead to this. So that would be where we take the 2 electrons here in this pi bond and we move it onto the oxygen. And at the same time, we take one of the lone pairs on this oxygen and move it here. And that's what will lead to that structure there. So then these 2 are also good contributors, well, significant contributors. We should think about them when we are thinking about resonance and thinking about what this molecule looks like. So we can put these in any order because it doesn't matter which one of these is more important out of the others. So we'll put that one right there, and we'll put this one right here. We have to draw out the resonance arrows that lead to each of these structures. So this one is just, we move the pi bond electrons onto this oxygen, and everything else stays the same. And then this one, we do the same thing, but we also move this pi bond. So then with a 5-word limit, we have to say why the major contributor, this one, is more important than the most important minor contributor. So the reason why is there are less formal charges. Everything is neutral in the major contributor, but there are charges on oxygen in the minor. And so that's not as desirable. It's not as bad as not having full octets like we have in the 2 additional significant contributors, but it's still like not preferred. So that's why for this one it says the most important minor is more important than the 2 additional significant contributors. So we're asking why is this one more important than these 2? And that's because of the unfilled octets. Okay, so not gonna lie, I got this next question wrong, and didn't understand it very well until recently, but I'm gonna try to explain it the best I can. So it's asking what is the number of conjugated p orbitals or pi orbitals, and how many of them are filled. So let's just look at this one right here. So how many p orbitals are contributing to this pi system? So in each double bond, there is a p orbital at each atom, and then there's also one that's contributing to this number of conjugated pi orbitals on the oxygens that are contributing to making and breaking double bonds. So there's going to be a p orbital here at this carbon and a p orbital here at this carbon, because those are what's making that pi bond. There's a p orbital at this carbon because it's participating in a pi bond between it and the oxygen, and it's also participating in one with this oxygen and also with the carbon next to it. And then there's one on the oxygen that's contributing to the carboxyl. And then even though this oxygen isn't contributing into any of the pi bonds in this particular major resonance contributor, it is participating in this pink one. Yeah, it's just participating in this pink one. So there's also a p orbital on this oxygen right here that is contributing to the number of conjugated pi orbitals. So there are 5 conjugated pi orbitals. And then how many of them are filled? So we're just going to figure out how many electrons are in these pi orbitals. So there's 2 here, 2 electrons, but there's kind of like, there's one filled pi orbital, because it could be like in here, or it could be in here, or it could be in here, or it could be in here, or it's kind of shared between either the top lobe or the bottom lobe in the molecular orbital. So yeah, there's 2 in this bond here. Actually, let's make this more obvious. Okay, so there's 2 here, there's 2 here, and then there's 2 on this oxygen. We can double check with any of the other ones. Again, if we draw the pi here, pi here, pi here, pi here, and pi here, there are 2 here. There isn't any on this carbocation because it's an empty p orbital, but there's 2 on this oxygen, and there's 2 on here. So you can double check that with all of them. By the way, there's 6 electrons in these conjugated pi orbitals, so 3 of them are filled at any time in any of these resonance contributors. Okay, so the last question on this page says to state the hybridization of each indicated atom on the structure. I'm not going to bother try to pronounce that. So the biggest thing to watch out for here is think about resonance. Like, that's the only thing that can really, well, not the only thing, but it is the big thing that can throw you off, because you could think that something's sp3 because that's what it looks like, but it's actually sp2 because you have to think about resonance where a lone pair can turn into a pi bond. So, starting with this oxygen, it has 2 lone pairs and 2 bonds, so you automatically think it's sp3. We have to double check, see if there's any pi bonds around or anything that could lead to it having resonance, and there isn't anything. These carbons can't participate in resonance with it. There's no double bonds here or there, so it's just going to be sp3. So that one's not tricky. Over here, again, there's 2 lone pairs on the oxygen, and then there's 2 sigma bonds. So that is sp3. No pi bonds around or anything that could participate in resonance. Remember that lone pairs, even though there's no lone pairs on these carbons, but you can think about it, there's no lone pairs that can turn into a pi bond. There's not a pi bond nearby that could turn into a pi bond, and there's not a pi bond that can turn into a lone pair. So that's why that is sp3 for that oxygen. This carbon, again, right here, same thing. There's nothing around that can contribute to resonance. This pi bond is too far if it was going to participate in resonance, which it can't. Over here, it would be a pi bond there, which isn't next to this carbon. So that's going to be sp3. Let me erase that so we don't think it's a pi bond. Oh wait, it is a pi bond. Anyways, so this one is the first one that is not sp3 because it only has 3 electron groups around it. It has this sigma and pi bond. It has the sigma bond and the sigma bond, so it is sp2. There's only 3 electron groups around it. This oxygen here, it has the sigma and pi bond. It has 2 lone pairs because it's 0 charge, so that is going to be sp2. Okay, so here's one. So the oxygen has 2 lone pairs and it has 2 sigma bonds. So we automatically think, okay, that's sp3, but no. So there is a resonance contributor where we move the pi bond electrons onto this oxygen. So then there would be a carbocation here, but we move at the same time the electrons from this oxygen right here to make a pi bond. So that would look like double bond, oxygen, oxygen, and so this oxygen would have a plus charge, this one would have a negative. It's definitely not the preferred resonance. We prefer it how it already is, but it is a valid resonance, and so we have to consider it. And so instead, this lone pair, or I guess you could say either of the lone pairs, but only one of them, can't be in an sp3 orbital. It has to be in a p orbital or pi orbital, so that it can easily move into resonance. And so the shape of this oxygen is actually going to be sp2, and one of the lone pairs are going to be in a p orbital so that it can move to resonance. This carbon is sp2 because it has 3 electron groups around it. It has each of these sigma bonds and then the sigma and pi bond for the carboxyl. And then lastly, this oxygen in the carboxylic acid group. Again, it's making a bond to that hydrogen. I guess I can draw that out. Hydrogen, lone pair, carbon, double bond to oxygen, and then the rest of this group. Again, this is the best resonance, but we can move this lone pair onto the oxygen, and we can move this lone pair right here to make a bond between the carbon and the oxygen. And so this lone pair has to be in a p orbital, and so the shape around the oxygen is sp2, hybridized. So that's page 3 of midterm 1.